This is Daniel Coosbury, and in a previous video, we introduced this idea of random variables, which gave us a bit of structure to work with probability problems and experiments and things. So this video is going to elaborate on that. We're going to look at some properties of random variables that we can apply to a lot of different kinds of problems and use to our advantage. So let's go ahead and start by talking about the expected value. So like in a data set, we can find the mean and standard deviation of a random variable, like I said, just like in a data set. The mean of a random variable x is also called the expected value of x, denoted by this capital E with x in the parentheses. So that stands for expected value. So in this video, we're going to refer to the expected value and the mean basically interchangeably. So we can, when we talk about finding the mean or finding the expected value, we're talking about the exact same thing. The expected value of a random variable may also be denoted by this symbol. If this variable is called x, for instance, then that's what we mean. So we use the Greek letter mu to refer to the mean, and then the capital X down there refers to the name of the random variable. So what we can see down here is the formula for the mean. So this should have an x by it. Sorry, this is a little sloppy. So the mean of a random variable x is the exact same thing as the expected value x. Again, that's that. And the way you find it is by taking each value that the random variable can take on. So that's what that x is. Multiply it by its associated probability, which is the probability of that x. And so you see these come in parentheses. This means you do the multiplication first. That's the pairwise multiplication. We've seen this in some other formulas like the weighted mean formula. And when we approximated the mean from a table, we use like the class midpoints and the frequency of those midpoints, or the frequency of those classes. So this is real similar. You take each value, multiply it by its probability, do it pairwise, and then add them all up. That's what the capital sigma is for. So I'm going to show you how to do this by hand, and then since this is a lot like what we've done before, there's a way to do it in the calculator that's identical to how we've done it before. So I'll show you that as well. So let's look at looking at the mean of a random variable. We have a computer monitor that's composed of a very large number of points called pixels. It's not uncommon for some of these pixels to be defective, so we're talking about defective things again. Let x represent the number of defective pixels in a randomly chosen monitor, and the probability distribution of x is as follows. So this is the probability distribution. This would mean there are 0 defective pixels. They all work. This would mean 1 defective pixel, or 2 defective pixels, or 3 defective pixels. These are the probabilities associated with that. We want to find the probability. We want to find the mean number of defective pixels. So we're looking for the mean of this random variable x, which is equal to the expected value of x. I'm just writing this so that you remember the definition. The expected value is the same thing as the mean. And this is found by taking each x and multiplying it by its associated probability, and then adding all those things up. So I'm going to go ahead and write it all out. So this means take 0, multiply it by the probability that you get 0. Actually, I'm going to write it like this first. The probability that you get 0 plus 1 times the probability you get 1 plus 2 times the probability you get 2 plus 3 times the probability you get 3. So that's like taking this formula literally. Take each of the values, multiply them by their probabilities. Now let's throw numbers in there. So the probability you get 0 is 0.2. The probability that you get 1 is 0.5. The probability you get 2 is 0.2. And the probability you get 3 is 0.1. Okay, so we got the pairwise multiplication now. So order of operation says, even written like this, you do the multiplication before you do the addition. So we're going to multiply all 4 sets of these before we add them up. So 0 times 0.2 is 0. 1 times 0.5 is 0.5. 2 times 0.2 is 0.4. 3 times 0.1 is 0.3. Add these up to get your answer. So 0.5 plus 0.4 is 0.9. Add 0.3, you get 1.2. This is the mean number of pixels in these monitors. So a little bit more than one of them on average. I'm sorry, not one of them. On average, these monitors have a little bit more than 1 pixel defective, which means like most of them have 1 pixel defective. Of course, that's like half of them, but this is the mean. I guess is what we're trying to say. So if it was possible to have 1.2 pixels, which it's not, like that would be the average number of pixels that are defective. Again, mostly one, a little bit bigger than one. So that's how we do that. You can do it in a calculator in a similar way. I'm going to show you at the end of the video how to do it in the calculator. I want to do another one. It's going to work exactly like this. And this example is meant to highlight what this phrase expected value really means. So when we say expected value, we mean like in the long run, how many would you expect? Okay, I'm just kind of writing everywhere now. How many would you expect in the long run? Another way to say this is on average, how many? Which is why the mean and the expected value are the same thing. But this is in this context, asking the question, how many would you expect in the long run, makes more sense than what's the mean? And even though you'd use the same method to find it. So let me read this and maybe that'll make some sense. Mineral economists estimated that a particular venture had probability at 0.4 of a $30 million loss. So there's the word loss, that's important. Probability of 0.5 of a $20 million profit, and probability of 0.1 of a $40 million profit. Let X represent the profit and find the distribution of the profit and the expected value of the profit. So I've already found the distribution down here for us. So we've got three different values that we could get from the venture. We could lose lose $30 million. That's the $30 million loss. See how that's negative? We could gain $20 million, or we could gain $40 million. Okay, so those are the three possible outcomes. The probabilities associated with those outcomes are given here. Those come straight from the problem. So 0.4 is associated with the negative 30, 0.5 associated with the 20, and 0.1 is associated with the 40. So this is our probability distribution. And look, it's discrete. There's three outcomes. One of them's negative. That's okay. The thing we got to check is the probabilities are all between 0 and 1, which they are. They should add up to 1, which they do. So this is a good probability distribution. It looks good. These numbers are paired well. The big question is, does this venture represent an expected gain or expected loss? Meaning, like, do we get with these numbers, do we go forward with this venture? Would we expect to gain something? Because if we expected to lose, there would be no reason to go ahead and like go forward with this particular venture, whatever it is, if we expect to lose things. But if we expect to gain things, it's still random. We could always lose $30 million. But if we expect to gain things, then we should go ahead and go through with it and hope, and the odds are on our side. So this is where the terminology expected value of X comes into play. So this, again, this is the mean. It's the same formula. But the word expected gain or expected loss makes more sense in context than mean, even though these are the same thing. So the expected gain is going to be, the expected value, period, could be gain or loss, is going to be X times the probability of X. And then same with the other ones. So then 20 times the probability of 20 plus 40 times the probability of 40. It's not cooperating. Okay, so you see that's kind of what we're going for here. So this is equal to negative 30 times 0.4 plus 20 times 0.5 plus 40 times 0.1. And I'm going to whip out my calculator for this one because I'm afraid of multiplying those numbers together wrong. So I'm going to do negative 30 times 0.4, which is negative 12. Keep going. Then I'm going to do 20 times 0.5. Well, that's just half of 20, so that's 10. All right. And then I'm going to do 40 times 0.1. That's going to move the decimal over and be 4. So on average, I'm going to expect to gain 2. So negative 2 plus 10 plus 4 is positive 2. Except, so does a gain of 2 really mean anything? Well, it's a gain, but here's the thing. I'm expecting to gain on average $2 million because my X is in million. This is negative 30 million. This is 20 million and so on. So this is my expected gain, which if you're a businessman or businesswoman, you might be okay with taking the risk and risking losing that much money but you would expect to gain 2 million, which in reality you're going to get one of that one or that one or that one. But on average, we're saying that you're going to get $2 million if you were to do this venture over and over again, or a bunch of ventures like this. You're gonna expect to gain this much money, which is good. So what I would suggest after running these numbers is say this is your expected gain. You don't expect to lose anything, even though there's a chance you do. I say go for it. If you got the money, I say go for it. So this is an example of why we would use the phrase expected value to talk about the mean when we could just say mean. I'm going to use expected value in this context, but really we did these problems exactly the same because these numbers, the mean and the expected value, are exactly the same. Just like a data set, we can find a mean. We could also talk about the variance or the standard deviation of a random variable. So like how spread out are the probabilities? Do they have a high middle? Do they look like a bell? Or are they skewed to one side? So we can talk about the variance and the standard deviation. These are formulas to find the variance. It's very similar to the way you find the variance of a data set. And the standard deviation of a random variable is the square root of the variance. So just note that the variance looks like sigma squared, but it has an x related to the random variable named x. So if we decide to call a random variable like y, then our variance of y would be sigma y squared. I hope that's clear. So this is just related to whatever we call the variable. If we call it b, then this would be a b. The standard deviation also has an x with it because of the random variable x. You just take the square root of the variance to get that. Now, I don't like using this formula. When I do the variance or standard deviation, I'm just going to use my calculator, and I'll show you how to do that. It's very similar to how we found the variance with grouped data in the calculator. So here's a probability distribution called x. It's right over here. There's no context to it. This is just it. It's a probability distribution. See, these add up to be 1. These are my outcomes, and I want to find the mean and the standard deviation of this. And I'm going to do it in my calculator. So the way to do this in your calculator, if you want to guess the first step, is to go into your lists and put this table into your lists. So I'm going to go into L2 and L1 and put these numbers in here. So in L1, I'm going to put my x values, which are 0, 1, 2, and 3. In L2, I'm going to put my probability values, which are 0.2, 0.5, 0.2, and 0.1. Now this should feel familiar because we did this with the group data. We had the midpoints and the frequencies. The frequencies we usually put in L2. The next thing I want to do is get out of here. I'm going to do a second quit. And I'm going to go to one variable stat, which is what we usually do when we have lists. And I'm going to let L1 be my list and L2 be my frequency list. So the probabilities are playing the role as the frequency list this time. If you've got the older version of this, you want to type L1 comma L2 like we've done before and hit enter. And this is going to give us our mean and standard deviation. So you see the X bar is 1.2. That's the number we found already. We already did this problem. We found the mean. So the X bar is 1.2. And we don't have a sample variance because this knows, based on the data, we're not dealing with a sample. So the sample standard deviation. We do have a population standard deviation, which we're going to use as our sigma x. So that notation is actually what we're supposed to use. So this is our mean, 1.2. This is our standard deviation, 0.87. So I would report that mu x equals 1.2 and sigma x equals 0.87. And that's the sigma x from the calculator. I don't even have an sx. If you noticed, sx equaled nothing. Like there's nothing there. It's because we're not dealing with data, we're dealing with probabilities. So just to remind you, if you have the older TI-83 or older TI-84, you're going to want to type L1 comma L2 into your home screen and then hit enter, and you'll get these results as well. So we could have done that to find the mean, the expected value for this problem. If we had put this data in, we would have got that X bar equals 2. If we had done it here, we would have gotten a 1.2, which I guess we already did that. So that's the same data set or the same distribution. So you can use distributions to find things in your calculator, and it's really handy. And so as I mentioned at the beginning of this video, having a distribution lets you do a lot of things with probability problems and experiments. The last thing I'm going to show you that you can do with the distribution is you can make it into a histogram. And the histogram is not too hard to make. So this is an example where we got the distribution and histogram for the number of boys in a family of 5 children, using the assumption that boys and girls are equally likely and that births are independent events. So this would mean in a family of 5 kids, I have 0 boys. In a family of 5 kids, I have 1 boy. This would be in the family of 5 kids, I have 5 boys. And so what you can see in the table that you can see more clearly in the histogram is the most frequent classes are these 2 middle ones. And then the less frequent ones are on the sides, and it's symmetric on either side, which that's believable if boys and girls are equally likely, and if births are independent, which they're not, but we're just assuming they are. Then you got this nice bell shape. And so you can use a distribution to make what's called a probability histogram. And note that the X's are labeling like at the middle of the bars, not on the ends like we've done with histograms before. The Y-axis are the probabilities. So you can see this is just above 3.3. So it's just above 0.3. It's 0.3125. So that's something else. In addition to finding like the expected value, like the mean and the variance of a probability distribution, you can also represent it visually, and that could be really helpful as well.